Good morning. Welcome to the Ethical Humanist Society of Chicago. My name is Svetlana Beckman, and I will be the moderator for today's program. Due to COVID-19, our programs are virtual for the time being. Obviously, we want to keep everyone safe and healthy. And of course, we look forward to resuming our in-person gatherings as soon as possible. For those who are new to the Society, we are a self-governing, inclusive, caring community for those who seek a rational, compassionate philosophy of life without regard to belief or non-belief in a supreme being. We focus on ethical values that bring people together, not on the beliefs that keep them apart. In the spirit of intellectual, philosophical, and artistic freedom, we come together to explore life, nature, and the universe. Like traditional religious communities, we celebrate births, conduct wedding ceremonies, and host memorial services. Through our Golden Rule Sunday School, we teach kids humanist principles, religious literacy, and critical thinking. We staff soup kitchens, pack lunches for the homeless, watch movies, and write fiction. And many of these activities, including the Sunday School, are taking place still, albeit virtually. Our Sunday morning programs give us an opportunity to learn about a wide variety of topics, such as current events, philosophy, art, and science, to name just a few. And today's presentation actually straddles, I would say, the area of science and the area of art, in that it's going to be a fabulously entertaining program. You'll see. And for those of you who have attended our virtual programs previously, the format is going to be somewhat different. Dr. Benjamin, our presenter, will have an interactive presentation. And so when he asks the audience, for example, pick a number, please do so and type it into the chat. And then I will convey it to Dr. Benjamin. And we'll go like this for about 20, 25 minutes. Then we'll, as is typical, break for intermission, and then open the floor and the chat for your questions for a good long period of time. All right, so now on to today's program. Dr. Arthur Benjamin is a professor of mathematics at Harvey Mudd College in Claremont, California. He is also a professional magician and has combined his two loves to create the show that you're about to see. Dr. Benjamin has presented to audiences all over the world and has appeared on many television programs, including the the Today Show, CNN, and the Colbert Report. He has been written up in the New York Times, USA Today, Scientific American, and People magazine. Princeton Review profiled him in their recent book, The Best 300 Professors. He has given 3 TED Talks, which have been viewed over 20 million times. He's the author of numerous books and DVD courses that share the beauty and magic of mathematics. His newest book is called The Magic of Math, Solving for X and Figuring Out Y. Reader's Digest calls him America's best math whiz. Please welcome the mathemagician, Dr. Arthur Benjamin.
Thank you, Svetlana. It's nice to be here, and welcome everyone. What a great audience that I can't see. This is going to be fun. Anyway, so good morning, ladies and gentlemen. My name is Art Benjamin, and I am a mathemagician. What that means is I combine my loves of math and magic to do something I call Mathemagics. Now, to get started, if you have a calculator with you, like if you have a calculator on your phone, bring it out. Okay. So I'll pause a few seconds so you can find your phones and calculating devices. It'll make it a little more fun. All right. And when you open up the calculator, let's make sure those calculators are working properly. Svetlana, I'm going to ask you to ask your audience to provide me with some numbers. All right. So starting with a 2-digit number, we want to make sure these calculators are working properly. Svetlana, would you give us a 2-digit number, please?
I will indeed. 23.
What was that?
23.
23. And another 2-digit number, please.
Let me see what I have because that was my own number. So let me see.
The first few numbers can be your own if you'd like.
Can be my own. Okay. 79.
79. Multiply 23 times 79 on your calculator. Make sure you get 1,817 or the calculators are not working. Is your calculator working?
Indeed, it is.
Great. Now, I noticed that took some people a little bit of time to get their answer. What I'm going to do is what I'll ask, let me show you I'm going to give you a shortcut for multiplying even faster. There's something called the square of a number, which most of you know is taking a number and multiplying it by itself. For instance, 5 squared would be 25. Now, on most calculators, there are little shortcuts for doing it. You could take 5, hit times and equals, or maybe you have an x squared button. What I'm going to try and do is to calculate it, square some numbers in my head faster than you can do on the calculators, even using the shortcut method. Okay, so Svetlana, we'll get started with a 2-digit number just to get warmed up here.
42.
42, 1,764. I know a lot of people like 42. It's the ultimate answer to life, the universe, and everything. But I have to confess, I've squared numbers for such a large fraction of my life that a lot of the 2-digit numbers I know by heart. So let's go up to 3-digit numbers. I don't have these memorized. I am actually calculating them. Give us a 3-digit number, please.
666.
Oh, I don't know where that number is coming from, but I get 443,556 on that one. Right? Here's another one that isn't quite so thematic, shall we say.
Okay, 179.
Okay, that should be 32,041. 32041.
I can see that our audience, that the audience is saying, is this a setup?
Exactly. Well, as I said, they're the ones providing the numbers. Let's do one more 3-digit number, then I'll push it up a level. Go ahead.
Okay, 655.
That's 429,025. 429.
Wow, says the audience.
Right. All right. Let's take this one step further. Going to try to square a 4-digit number this time. Now, I will not beat you to the answer on this one. I will try to get it right. And just for my own short-term memory, I will write that 4-digit number down as we go along. Okay. So, Ray or Svetlana, if you would give me a 4-digit number, I will do it. Okay. So Ray is sending me the number 4901. Okay, 4901. Here we go. I'm going to try and square this in my head. I get 24,019,801. Good. Thank you. All right. Let me try one more thing, and let's see. Again, if you have a calculator on you, let's take. I want you to let's do the following experiment.
I'm so sorry, my computer. As computers are wont to do. My apologies. I'm back.
You're back. We had fun without you. Don't. Good.
I'm glad.
We squared a 4-digit number. Let's.
Okay, very good. I'm back in the game.
I'm gonna try something a little different. I want you to enter on your calculator a 1-digit number. Okay, this is for everyone in the audience. But Svetlana, I want you to do it for sure. Enter on your calculator a 1-digit number. Okay. Multiply that by another 1-digit number. Okay. Multiply that by another 1-digit number, and keep multiplying by 1-digit numbers until you have a 7-digit answer. Okay. So you should have as an answer. Well, you'll have a 7-digit answer when you're done. All right. Let me know when you've reached that point. All right.
Okay.
All right. Now, so there's no way I could know what 7-digit number you have, or anyone in the audience for that matter. Svetlana, I'm going to ask you to, if you would, to call out for me any 6 of your 7 digits, any 6 of them in any order you'd like, 1 digit at a time. I shall try and determine the digit you left out. Okay.
All right. So you want 6? Okay. Very good.
Any 6 of those 7 digits, and you can call them out in any order.
Okay, 418110.
I heard 5 digits. 41810. Okay. Concentrate on the digit you left out. Doesn't do any good, of course, but it looks dramatic here. I'm getting a lot of nothings, Svetlana. You didn't leave out a 0 there, did you? That's why we get a lot of nothing. That makes sense. Okay. Thought it was me, but it was 0. That's sometimes. Yeah. I'm willing to do that with another person from the audience if they want to type in 6 of their 7 digits. No guarantees here, but because
okay,
more remote.
I'm waiting for someone to type in a number.
Right, and don't leave out a 0 because that's like nothing. So I've already dealt with 0. If you call it, we'll call it 6 of your 7 digits.
Okay, right. So here we go. 326960.
I believe that person left out the number 1.
Let's look at the comments. Yes.
Fantastic. Okay. All right. Let me switch gears. On something else here. All right. So this one, by any chance, does anyone here happen to know? And this is a question for the audience. Does anyone here happen to know the day of the week that they were actually born on? Now, normally, I'd ask them if raise your hand if you know. Svetlana, do you happen to know the day of the week you were born on?
No idea. Okay, no idea.
Right. Well, maybe if someone in the audience, what I'm going to ask them to do. All right, Ray says that he knows. All right, Ray, what I ask you to do is to give us, if you're willing to share with us your birthday, including the year. I will try and determine the day of the week that it happens. So don't tell me the day of the week. That's what I'm going to try and figure out. Okay, so so I see 1987, January 13th. Was that a Tuesday? Excellent. Yes. And does anyone else want to give it a try? They anybody else happen to know? Want to give it a? Okay, 1970. May 10th was also a Sunday. Look at that. All right. Yeah. All right. And Mother's Day. Sherry says it was Mother's Day. Indeed, it was Mother's Day in more ways than one, wasn't it? All right. I'll tell you what. You know what? At this point, I'm gonna take a little bit of a break. Let you do whatever you need to do to switch gears. And for the remaining hour or so, I'm going to take your questions about anything at all. All right. So, but Svetlana, let me move this over to you so you could do whatever commercial breaks you like to do, and take it from here.
Excellent. All right, so we have arrived, and I do apologize for my disappearance there. But anyway, we have arrived at the Q&A. Obviously, it's going to be a very lengthy Q&A, so I can think of about 10 questions already that I want to ask. So you'll have to battle me for them. But first, we will listen to a brief musical interlude, look at a slideshow of past ethical societies, programs, and collect donations. Contributions will be collected virtually at ethicalhumanistsociety.org/donate or with Zelle to donate@ethicalhuman.org. Zelle rhymes with, oh, I'm sorry, I'm not supposed to read that, that it rhymes with the L. We suggest a donation of $5. And of course, appreciate any amount that you're comfortable with. It is through your generosity that we show how meaningful the Sunday programs are. And thank you for everyone, or to everyone, for sustaining the society with donations of time and money. And I believe that all of this information is typed into the chat. So please go ahead and support us. Thank you. We're back. All right, we have, I'm surprised that the first question isn't, how do you do this? But all right, here is the question. As a past math teacher, I wonder how you balance having fundamental math serve as a hook for engaging with math versus further othering those who don't get it. Huh, interesting.
Yeah, I'm not sure I understand this question, but I mean, the goal of my presentations, whether I'm performing for an advanced audience such as this one, or a more elementary audience such as an audience at an elementary school or a middle school, the goal of my presentation is not for people to see how smart I am, but how smart they can be. Right. So I like to teach people, I don't know, I would say fun methods, you might call them tricks, that allow you to do math in your head faster than you might do with a calculator. I think it's very empowering. I'll give you an example of this, especially for the youngest members of the audience who are watching this, because this is a fun little trick to do. And again, for some reason, they don't show you this in school. Now, when I was a kid, my favorite two-digit number to multiply was 11. And of course, it's easy to multiply one-digit numbers by 11, right? 3 times 11 is 33. 4 times 11 is 44. But there's also an easy way to multiply two-digit numbers by 11. So let me give you an example. Let's take a small two-digit number. I'll throw out this number. Let's say 23. All right, 23 times 11 is as easy to do as 2 plus 3. 2 plus 3 is 5, and that's your answer, 253, 253. Let's try another one. Let's say we wanted to do 62 times 11, right? Now 6 plus 2 is 8, and there's your answer, 682. All right, one more. All right, shout it out to yourselves as soon as you get it. Right, try and do 81 times 11, and you get 891. Exactly. All right. So now, before you get too excited, I've only shown you half of what you need to know. Because what if the numbers add up to something bigger than 9? Suppose we had a problem like, let's say 85 times 11. All right. So 8 plus 5 is 13, but the answer is not 8, 13, 5, right? There's we only have room for the 3, but the 1 makes the 8 carry, and the answer is 935. All right. So here, let's do just two more examples. Say 57 times 11, right? 5 plus 7 is 12. So what's your answer? 627. Last one. This one I want you to try. Really, really try it, okay? In your head, see if you can multiply 77 times 11. All right? What do you get? I hope you got 847. Give yourselves a nice round of applause. All right. So that's just a sampling of what I like to do to empower people to say, wow, math can be fun. You know, I can do this. I can do something maybe that my parents can't do yet. Right. I think that these methods have broad appeal both to the students that get math and are a little bit bored and unchallenged by it. They see new strategies, and maybe for people who never saw what there was to enjoy about math. I try to inject that wow factor into it. All right. Next, Svetlana, next question. What else would you like
so I'm gonna skip the next question in the chat and take the prerogative of the moderator. So the secret to what you have shown us, is it that there are certain rules for combining numbers that an average person is not aware of, hasn't been taught? Or is it that you're able to visualize you're able to see what I would write on the piece of paper when I'm manipulating numbers, or is it some combination of the two? Like, what is the secret here?
It's more the first thing you said than the second, because I am not visualizing anything. If in fact, maybe this will come as a surprise to most people, I'm not seeing the numbers in my head. It's much more accurate is that I'm hearing the numbers. All right, I'll give you an example. If I ask everyone in the audience, so what is 3 billion plus 4 billion? You all say 7 billion. And it's not because you saw that 3 with 9 zeros followed by 4 with 9 zeros and started adding them up. I think most people, what they do is they say, well, 3 plus 4 is 7. And the word billion comes for the ride, right? So when I'm doing the math in my head, and maybe the most important fact to remember about as far as my methods go, is I do all of my calculating from left to right. And that's the opposite of how you may do it on paper. On paper, you do it from right to left, right? You get the ones digit, then the tens, the hundreds, the thousands, but that's backwards. We read numbers from left to right. We pronounce numbers from left to right, right? We say 935, not 5 and 30 and 900. And with a little practice, you can and should calculate left to right. The reasons behind these methods are pretty simple. If you and especially with algebra, it makes for great motivating material for learning algebra. But here's one that doesn't require any algebra. When we were saying, why does the 11s trick work? Okay, if you were to say 23 times 11, right? Now, what was I saying? I said you do 2 plus 3 is 5, and that's the answer, 253. But what is 23 times 11? Well, it's taking 23 times 10, which is 230, and then 23 times 1, which is 23. And if you were to add these numbers, 230 plus 23, it's going to start with a 2, it's going to end with a 3, and what are you going to have in the middle? The 2 plus the 3, right? 2 plus 3 is 5, and that's your answer, right? So like I say, math is not just solving for X, it's also figuring out Y. And what a mathematician gets very excited about is not just the final product of the answer, but the process in which that answer was derived. That's one of those more subtle joys of mathematics that the mathematicians get really excited about. Why is that true? It's great to find and discover these beautiful number patterns, but we want to understand why. And we want to understand it from maybe several different perspectives. So,
awesome. All right, here's a question. What is your favorite math constant?
What was my favorite constant? Oh gosh, it's like asking me to pick my favorite child, but I'll give you a few of them, okay? And I could elaborate on any of them. When I was little, I liked little numbers. My favorite little number was the number 9. 9 is a very magical number. In fact, one of the tricks that I did for you earlier today actually was based on the number 9. And when you as you become a teenager, you become a little bit more irrational, and you find yourself falling into numbers like pi, of course, or e, or the golden ratio 1.618. I could riff on any of these numbers, and of course, you go to college, you start finding yourselves falling into transcendental numbers and imaginary numbers and great numbers like that. When the number I liked, and if you'd asked me in middle school, the number I liked the most was 2,520. Everybody has a favorite number, right? And I'll throw that out as a challenge to the audience. If anyone in the chat can figure out why I like what's special about the number 2,520. What would make that such an interesting number to somebody who liked numbers? Let's see if yes, it is a multiple of 9. I'll give you that. But of course, there are lots of multiples of 9 out there. But what else is special about 2,520?
I will check the chat and see what folks share.
Okay.
We'll move on to another question,
Yeah.
which is, I understand that you prefer to emphasize the study of statistics prior to or in favor of calculus. Why?
You know, I think that too much of our math education in high school is pushing people in the direction of calculus. That is, I mean, we spend many, many years learning arithmetic. Then we learn algebra, which is fundamental to all of mathematics. And then for the next few years, all the math we're learning is pushing us towards one subject, and that's calculus. And yes, if you go on to a career in science, engineering, economics, you are going to need calculus in your studies. But for day-to-day use, and I'm a math professor, I don't, outside of my research and my teaching, I don't use calculus on a daily basis. I mean, I will say a daily basis, almost ever. I mean, I just can't think of when outside of my career as a professor, ever used calculus in my daily life. On the other hand, statistics and probability, that's something that you can use on a daily basis. I probably apply probability. You probably, maybe subconsciously, apply probability and statistics every day of your life. You're looking at data and trying to make decisions about that. You're weighing risk. Anytime you make a decision, should I do this or should I do that? You may well be applying ideas from probability and statistics, and the better you understand that, the better kinds of decisions that you can make. So I think that if it were up to me, I would rather every student graduate high school having had some exposure to probability and statistics and data, and some calculus, or for those who are inclined, those who want to go in a scientific direction. But to me, we would have a more, I think people would see the point of mathematics more if they were exposed to probability and statistics, especially if it's taught well. I mean, it can be a lot of fun. It is, it's understanding games, gambling, risk, reward, money. Is very much tied into probability and statistics. I think you'll get people's attention. Anyway, so that I'll step off my soapbox. But yeah, if it were up to me, I would want statistics to be the preferred mathematics capstone.
I couldn't agree more. Just on a personal note, we were just picking classes for my next year senior in high school, and the only statistics class that's offered is AP statistics, advanced placement. And he's just, anyway, he's not on that level. But if it was a regular level statistics, I would make him take it.
Absolutely.
Anyway, it's too bad.
Mathematics of games and puzzles. I mean, unfortunately, it's more than just a choice that you as a parent has to make, or your school. It really has to be embraced sort of at the national collegiate level, because my daughter, who's now a college senior, my oldest daughter, and had very strong interest in psychology, and indeed will be graduating with her bachelor's in psychology this spring. And of course, she wanted to take statistics, and everyone at the high school was pushing calculus. They say, no, it's going to look better on your college application if you take calculus. It's a more impressive sounding course. I said, but she took calculus in her junior year. She wants to, take something new. And they say, no, take the second calculus course. Like, no, she's had enough of calculus. And ultimately, she prevailed and took the statistics course. I said, any college that doesn't take you because you decided to take calculus and statistics instead of calculus and yet more calculus doesn't deserve you. So happily she got into her top choice and all is well. But yeah, it's a fight, and it's one that has to be embraced not only by the high schools and the parents, but also by the colleges, to say take 4 years of interesting mathematics as opposed to, follow this prescribed path.
Great. All right. Speaking of what we are force-fed in high school, why did I learn quadratic equations? What are they good for?
It's very funny. I remember when my daughter was in 8th grade. I was out of town giving one of my shows, one of my mathemagical shows, and I had the and I was talking to my wife, and she said, yeah, today they learned about the quadratic equation, and she wanted to know why. And I said, oh, I wish I could have been there. I could have derived it for her, completing the square and all. I said, no. She didn't want to know why it worked. She wanted to know, why are we learning this and what is it good for? I was crushed. I thought she wanted to know why it worked. We put in I'd say an undue emphasis on equations like that because we can calculate with them. It's something that, how does the saying go? If you can't measure what you value, then you value what you can measure, right? That is, these are questions you can put on tests. Where do we use quadratic equations? Yeah, as a mathematician, I can see lots of times when we actually are interested in solving equations, whether it be, in calculus, for example, if we want to sometimes determine what the optimal pricing point is for, what will allow you to make the most amount of revenue. How should you, if you know how the demand varies with the supply, with the price, what's the optimal price you should pick so you make the most money? Okay, I mean, a question like that will likely involve solving a quadratic equation. I think it's, but I don't think we need to hit them over the head with it and do it for weeks and weeks at a time. But that's actually one of the more useful things that they teach you, believe it or not. There are some things that I see there's a lot of, in my opinion, junk in our curriculum that I just don't think they're ever going to use, or if they're ever going to use it, it's going to be so specialized, and they'll already be at a sophisticated mathematical level that they can figure out, what the point is. So I think there's definitely room in our curriculum to teach them math that is fun, more motivated by games and puzzles. Who doesn't like games, puzzles, magic? I mentioned statistics the other day, probability. I use probability every day of my life when I'm not teaching and speaking. My favorite hobby is the game of backgammon. I play backgammon online literally every day, and I am using techniques of counting and probability and weighing the odds in every match that I play. And so it's great fun.
Have an answer to the question that you posed. What is special about 2,520? And it is that it's 50 squared.
And that's not right, because 50 squared is 2,500. So you're off by 20. Right? So but I think I saw an answer in the chat that was closer. What did you get from there? Did you see someone else?
Did someone, that may have been, I did not see it.
Somebody said after the 50 squared, I saw Sherry post, it's the smallest number divisible by all integers. And it is indeed the smallest positive number that's divisible by all the integers from 1 through 10. So it's divisible by 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, not 11. But yes, that was good for whoever saw that. It was why that was my favorite number.
Excellent. Can you do any geometry tricks?
Oh, that's a good question. Do any geometry tricks? I don't have with me. There are some cool tricks where you take where you could take an 8x8 square, 64 squares, and cut it into 4 pieces, rearrange those pieces, and create what looks to the unaided eye like a 5x13 rectangle. And that 5x13 rectangle, if you think about it, has an area of 65. So how if we turned something with an area of 64, rearranged it, and get something with an area of 65? And the answer turns out to be that when you've cut things in and redistributed them, there is a tiny, at one point you have 2 triangles next to each other, but those triangles aren't exactly, they don't exactly have the same slope. And there's a little bit of space between these 2 triangles. And though your eye can't really detect it, but the accumulated amount of area in that little space is 1 unit. And so that's where the 5x13, that's where that extra 1 unit comes from, with 65. So I'll leave it at that. I wish I had one of my geometrical magic tricks with me, but that's the essence of it. If you're interested in that sort of thing, you could search on the word mathematical vanishes or geometrical vanishes, and you can see some very creative examples of that.
Thank you. What inspired you, and how did you come to create Mathemagic?
Well, if as a kid, I liked showing off. You probably can't tell that about me now, but as a kid, I loved I was just trying to impress one way or the other. And I got into magic. I mean, what kid doesn't? Most kids outgrow that at some point, but I didn't. I stayed with it. Stephen Colbert thought, the math and the magic, I just combined the nerdiest stuff out there, and that's absolutely true. I mean, if he had known me in high school, I was captain of my chess team. I mean, what could be more nerdy than that, right? Backgammon, but anyway, I would did magic shows for kids. I grew up in Cleveland, by the way, so not far from Chicago. I appreciate the same weather that you have, and I did magic shows for children's birthday parties throughout the east side of Cleveland. I was the great Benjamini, and magical fun for a very low fee, and that was. And I did that for years, and as I started getting requests to do shows for older audiences, for adults, my father suggested I put some of my math into the show. That I would, on my own, I always had a fascination for numbers, and I figured out some ways of calculating quickly. And I'm happy to explain to you, if you're interested, how to square numbers, for example. And he said, I've always been impressed by that. And he would show me off at parties now and then. And he said, well, I'd put that into the show and see how that flies. And to my surprise and delight, it got the best reaction of the show. So I said, wow, well, if they like that, imagine if I could do these problems even faster, or I attempted bigger problems. And it just kind of grew from there, and it got a certain amount of publicity and attention. And eventually that became my show. So the great Benjamini hung up his magic wand decades ago, but I've been performing this Mathemagics show, since I started college. A little background, by the way. As I said, I grew up in Cleveland, Ohio, and went to Carnegie Mellon University in Pittsburgh for my bachelor's degree, Johns Hopkins University for my PhD in applied mathematics, and I've been teaching at Harvey Mudd College near Los Angeles, California, in Claremont, California, since 1989.
So Adam, age 5, is asking.
Adam, one of my favorite names. Do you have a sister named Subtractum? Sorry to hear that. Okay, what does Adam ask, please?
Adam wants to know, what is the biggest number you know?
The biggest number I know. Every now and then I think of the biggest number I know, and then I add 1 to it, and then I have an even bigger number that I know. So that's one of the fun things. I mean, you could talk about infinity. Now, infinity isn't really a number; it's kind of a concept. I talk about infinity forever, but there's I'll give you some of the biggest numbers that I can say. So, for example, there's the number Google, which is spelled Googol, and Google is a number that starts with a 1 and then has 100 zeros after that. So that's more than a trillion. I mean, it's so big that there are more that Google is bigger than the number of atoms in the universe. I mean, it's that big a number. But conceptually, you could think of a bigger number, right? You could think of Google plus 1 or Google times Google. That would be a number with 200 zeros after the 1. Or, and this is maybe the biggest number that you can say quickly, it's called Googleplex. And Googleplex is 1, not followed by 100 zeros, not followed by 1,000,000 zeros. It's 1 followed by a Google number of zeros. You could not even write that number down, even if you had a book as large as the universe. You wouldn't be able to write a Googleplex down.
Wow. You're reminding me of an episode in the original Cosmos, I think, where Carl Sagan talks about Google and Googleplex.
Oh.
I'll have to find that one.
Yeah.
Okay.
By the way, the company Google has their headquarters, their center is called the Googleplex. So now you know.
All right. For something completely different, what do you think of Bitcoin?
Yeah, I'd say if you're a young investor, put some money into it. Don't throw all your money into it. But if you're nearing retirement, don't stay away from it. But if you are young, you have a little bit of income to dispose of, take it as a long shot and see if it grows spectacularly. So it might fail, but it might blow up. So I would say, if you're young, you're in your 20s or 30s, put a little bit of money into Bitcoin. And if you make a ton of money, remember you heard it from me, and
pay you a finder's fee or something like that.
But if you lose it all, you never heard it from me.
What's a good source? How can one understand Bitcoin? A layperson, even a person who has some math. That's the challenge. I mean, it sounds.
Yeah, study economics. I mean, in some states, why do we value $1 bills or $100 bills? I mean, they're just like a cheap piece of paper, but a system that people trust has been, and governments have backed this idea that if I give you this piece of paper that has a picture of Benjamin Franklin on it, you're willing to give me goods and services in return. So what's special about that piece of paper versus some other system that people have come to accept or trust? So, I think it's worth a shot. But again, it's in the same way that what if people say, "Wait a second, what are all these pieces of paper doing? What if you're scared of dollar bills, what are you have to put your faith in something." So,
I think someone asked earlier on how, and I may have missed you doing square roots, but is there a trick for doing square roots?
So you saw me do a lot of squaring, which is taking a number like 5 squared is 25. The reverse of that process is the square root. That is, if someone says 25, its square root is 5. 36 has a square root of 6. Now the problem is 37, has a square root of, I don't know, something smaller than 6.1. And so if the number you get is a perfect square or a perfect cube, or say the number is a perfect square, if you took a 2-digit number and squared it, I could tell you what the 2-digit number is. Take a 3-digit number and square it, I could figure out what the 3-digit number is. But if it's not a perfect square, then all you can come up with is an approximation of these answers, because these numbers are irrational numbers. They're infinite number of numbers after the decimal point. So all I can do is give a good approximation of that. Now, the way I do that is something called divide and average. So for example, someone said, what's the square root of 37? I say, well, 6 goes into 37. If I do the division, it's 6 and 1/6. Right? You get 6 with a remainder of 1. Then you divide 6 into 37. So 6 and 1/6. And now if you take the average of my guess, 6, and the quotient, 6 and 1/6, their average is 6 and 1/12. And that average will be very close to the square root. It'll always be a tiny bit high. So 6 and 1/12 is 6.083333. I'd say it's about 6.08. Right? And if you do the square root of 37 on your calculator, it will begin 6.08. Okay, so that's my process. It's called divide and average. For those that have taken calculus, this is actually a special case of Newton's method, but that's all I'll say about that.
Huh. How did you do in school? I wonder if I understand that question. Showing your work. Yes. Showing your work is the questioner's least favorite part of math. And I suppose they are asking, how did you feel about it, and what do you think of it?
That's a fantastic question. And when I speak in front of, say, audiences of gifted children and their parents, the parents are always, that's a question I always get, my son or daughter refuses to show their work. They want to do it all in their head. And it took a very strict math teacher in 11th grade to break me of that habit. I sort of prided myself of doing all the math in my head. I remember once answering a question on an exam, and I just wrote down the answer, and I got very little credit for it. And I said, "What?" He said, "You did that all in your head?" I said, "Yes." He said, "Well, then you're a better man than I am." And I wanted to say, "Well, then, as your superior, I ask you to give me the credit I deserve." But seriously, the reason it's important to show your work is because mathematics is not just about getting the answer. It is about understanding the process to which we get to the answer. And if you want to appeal to the ego of your son or daughter who refuses to show their work, here's what I'd say. In the in the real world, if you want to make a lot of money with your mathematics, they are not paying you the big bucks for your answers. They're paying you the big bucks for your explanations, right? Someday you will work for somebody who is not as smart as you are, right? And you can't just say, yeah, here's my answer. It's 6.08, and trust me. They say, no. I want your boss say, you have to convince me. Why is this true? So so showing your work actually deepens your own understanding of the process that you're going through. And it makes you a better problem solver, and it makes you a more valued employee, that you can communicate and convince others to use your solution. Right? So show your work. As much as I like doing math in my head, show your work.
Okay. And by popular demand, please teach us another Mathemagic trick.
All right. Okay, bring out your calculator. And I want you to take a, I want you to think of your favorite 4-digit number. Okay, I mean, this could be maybe your PIN number or last 4 digits of your credit card number, whatever, some 4-digit number. Don't make it too easy, like 2222, something more interesting. Okay, and I want you to enter that on your calculator as an 8-digit number by repeating it twice. So for example, if your PIN number was 1234, which I don't recommend, then you would enter on your calculator 1234, 1234. Okay, so you have an 8-digit number. Okay.
Okay, and I'm going to have the audience do it. I'm not going to do it. Somebody in the audience is
Oh,
going to
well, all right. Well, I want you.
That's okay. I'll do it. I'll do it. I got it.
All right. So, but I want everyone in the audience to do it. So take that. So you should all have an 8-digit number that looks like ABCD, ABCD. Okay. Now I told you my favorite number when I was a kid was the number 9. So go ahead and divide that number by 9 on your calculator. Hit equals, of course. And now you have a number, probably has some stuff after the decimal point. Let's make sure of that. Divide this number by 9 again. Now, unless you're very unlucky, you have some complicated number, probably a 6-digit number with stuff after the decimal point. Let's see. Now I want you to divide by your original 4-digit PIN number. Okay, so divide it by, if it was 1234, divide that number by 1234. All right, so you should now have probably a 3-digit number followed by stuff after the decimal point. Okay, I want you to concentrate on that number. I can only see you, Svetlana, but I'm going to try and get it here. Svetlana, it sounds to me like you're counting. I hear 1, 2, 3, 4, 1, 2, 3, 4. Oh, there. I see what you got. You have something like 1, 2, 3.469, something like that. Got it. Okay, now I see what's going on. And oh my gosh, I think a lot of other people got that one too, right? Okay. Check
it. Touche. So now tell us how, right? We don't just want to see the trick. We want to understand the trick, if you don't mind.
And it's very interesting because as a magician, of course, we don't like to, we're told not to explain our secrets, right? And the reason magicians don't explain their secrets is we've all made that mistake before. We tell someone how a trick is done and we hope people go and say, wow, that's clever, you're good, but you never do. I mean, how have you reacted most of the time that someone's taught you a magic trick? It's usually like, oh, that's dumb. I thought you were good, but I just wasn't paying attention. And that's true about most magic tricks. They're based on usually a very simple idea. But you asked me so nicely, Svetlana, I will explain to you how I did it. But just remember how impressed you were before I gave you the explanation. Okay, hold on to that feeling. All right. So what's going on when you take a number? All right, let's take a number like 1, 2, 3, 4, 1, 2, 3, 4. Okay. Well, if you think about it, that's equal to 1, 2, 3, 4 times 10,001. Right? Because 1, 2, 3, 4 times 10,000 would be 1, 2, 3, 4 followed by 4 zeros. And then when I add 1, 2, 3, 4 times 1, I get 1, 2, 3, 4. All right. And now, what did I ask you to do? I said, take that number and divide it by 9, and then divide it by 9 again, and then divide it by your original number, in this case, 1, 2, 3, 4. And notice what's happened. That 1, 2, 3, 4 has been divided by that 1, 2, 3, 4. And so all that we're left with is 10,001 divided by 9 and divided by 9 again. And you could check on your calculator that you'll get 123.469, something like that. Okay. So again, it's easy once you know the secret. Aren't you disappointed?
This, it is said that somehow science, when phenomenon that looks mysterious is explained by science, the phenomenon is cheapened. And I don't feel that at all. Just as with this demonstration, I'm more impressed. It adds an additional layer, right? Rather than taking away from what originally seemed just magical. So
Absolutely. If I mean, and I couldn't agree more. And I think we should use more magic in our teaching as a way to get people intrigued about this. By the way, one of the greatest proponents of this was a fellow named Martin Gardner, who was, I would say, was the ultimate and certainly the original and the best mathemagician out there. He was a science writer for Scientific American. You know him from his work with the Skeptic Society. He and he was a magician. He knew more about card tricks than anything else, but also was an amateur mathematician and just had a knack for explaining things and putting things in a way that would inspire others. I was one of those people inspired by the work of Martin Gardner, who, by the way, was an undergraduate at the University of Chicago himself. So another connection to your organization. But yeah.
Let's see, many questions. Oh, interesting. Do you see differences in young males and females learning math?
I teach at the college level, so I don't get to see as many children as they grow up. My understanding is that boys and girls do about the same in mathematics until about the 6th grade, where I think it has more to do with social pressure than any of the hormonal or biological pressures out there, where they're I don't know how I want to say. I think sometimes you see some of the confidence in women starting to ebb a little bit, and it shouldn't. But I'd say boys are more likely to blurt out answers. I was a blurter myself in middle school and elementary school, and they could shout out answers even whether they're right or wrong. Women tend to be more thoughtful, want to make sure they know what they're saying and doing before they blurt it out, but there can be an intimidation process that happens. I think women who have had whose math, if when classes have been segregated into boys' classes and girls' classes, the girls do tend to perform better without the social pressure and maybe even the physical blurting out pressure that comes from the co-ed classes. So the high school that both of my daughters went to were they had classes separated through 10th grade. 9th and 10th grade were separated. 11th and 12th they came together, and I think that's not a bad system. So my belief is that everyone has the same and tremendous potential for doing and understanding and enjoying mathematics. Unfortunately, there are societal pressures that have pushed things in weird directions. But we've seen a lot of improvement over the years. I mean, in that, the 50 years ago, there were almost no advanced degrees in mathematics given to women. Now it's somewhere close to 40%. We're still approaching that asymptote of 50%, but we've come a long way. But there's still progress that needs to be made.
Ray, who shares his age as 33, asks,
I knew that.
What the heck is with imaginary numbers? Is there an everyday use for them?
That's a great question. So, for those that don't know about imaginary numbers, there's a number called I, and the square of the number I is -1. And you go, that makes no sense. How can the square of a number be -1, right? I mean, if you square a positive number, you get a positive number. If you square a negative number, you get a negative number. You get a positive number, right? -3 times -3 is +9. So how can a square of a number be negative? Now, before I answer that question, think about even the idea of a negative number was considered impossible by most people for centuries, for millennia. You know, even mathematicians couldn't get their head around a negative number, right? What does it mean for a number to be less than 0? How can you have, what's the idea of -5, right? How can a number be less than 0? And eventually, the idea that made sense was to say, well, we can think of a number line with 0, say, in the middle of that number line. And to the right of 0, we have the positive numbers. And to the left of 0, we have negative numbers. And so if you just restrict yourself to the numbers that you can measure, the numbers that you can see, you might only see the numbers to the right of the line. But once you see the whole number line, then you say, oh, okay, so negative numbers mean less than 0 means really to the left of 0. Okay, that kind of makes sense. And eventually we came up with applications for it. Like, what does it mean to have -3 apples? It might mean I owe you 3 apples, right? But now let's get back to the question, what about imaginary numbers? Well, first of all, where do they live? You can't find the imaginary numbers anywhere on this line. And the answer is they live on this line. They live on a line that's perpendicular. Here's the number 1i. Here's the number 2i, 3i. 3i times 3i is -9. It's 9i squared. By the way, below 0, you have -i, -2i, -3i. And there's all kinds of beautiful mathematics that's based on imaginary numbers, or even things that are called complex numbers. Like, what do you get when you add 3 plus 2i? You get 3 plus 2i. That's called a complex number. That lives here on the plane, on what's called the complex plane. Now, you might say, okay, I can sort of imagine what -3 apples means, right? But what does a 3 plus 2i mean? How does that help us? And the answer is that a lot of complex numbers, imaginary numbers, can be very real. For example, the most effective description of electricity and magnetism actually uses complex numbers. I can think of some real problems where the question is real, the answer is real, but the way we get from this real answer to this real answer is through complex numbers. Perhaps where they get applied the most is there's something called the fundamental theorem of algebra. And somebody asked about the quadratic equation before. They go, what the heck is a quadratic equation? Are there equations that can't be solved, right? And so, like, take the equation x squared equals -1. Does that have a solution? Well, if you only know about real numbers, no, there's no number where the square is -1. Or we could write that as a polynomial, x squared plus 1 equals 0. There are no real solutions to it, but there are imaginary solutions, complex solutions to it. And the fundamental theorem of algebra says if you take any polynomial, whether it involves x squared or x cubed or x to the 4th or x to the 20th power, there's always at least one number, and it might be a complex number, that you can plug into that polynomial and get 0. That's called the fundamental theorem of algebra. So that gets applied a lot. And beyond that, I think we're beyond the scope of this lecture. But yeah, complex numbers, imaginary numbers, can be very, very real. And I have a whole chapter on. In fact, here's an equation. I'll give you one last motivation for this. Is every few years, popular science magazines have asked their readers for what they consider to be the most beautiful mathematical formulas or equations. And almost inevitably, the equation that tops the list is this one. It says e to the I pi plus 1 equals 0. E to the I pi plus 1 equals 0, where E, and I've even heard this referred to as God's equation, if the Humanist Society will forgive me for that, because here in one formula, you have maybe the 5 most important numbers in mathematics, right? 0 and 1, which are the foundations of arithmetic. E is the most important number in calculus. If you ever took calculus, you saw the function e to the x all over the place. Pi, which is the most important number in geometry, and I, which arguably is the most important number in algebra, all put together in this rather beautiful formula. Very simple, but what does it mean? Here's what it means. All right. Now, I showed you the complex plane a minute ago. Here, I'm going to draw it again through the number 0. Right there, where the real axis and the imaginary axis combine, is the number 0. Over here is 1. Here's -1. Whoops. Yeah. Here's the number I. There's the number -I. This is the unit circle in the complex plane. And if I ask you, what is the circumference of that circle? You say, oh, it's 2 pi, right? The circumference of a circle is 2 times pi times the radius. Radius is 1, so the circumference is 2 pi. Suppose I don't go all around the circle, I just go pi around the circle, okay? If I go pi units around the circle, right to there, then what number do we land on? We land at the number -1. And that's what this is saying. E to the I pi is equal to -1. All right. And so that's I think it's beautiful. It's intriguing. Maybe makes you want to understand mathematics more. If you want a more general equation, the great mathematician Euler showed that if you take any angle theta, e to the I theta is the cosine of theta plus I times the sine of theta. So this number I gets used in trigonometric calculations. That was another reason why complex numbers can be useful. And here's a fun one. If you want, for those with more math in their background, if they want to try a fun little challenge, is what do you get when you take I to the power of I? And the answer is you get something real. You get e to the -pi/2, which it also deserves, should be another one of those beautiful equations where we're combining e and I and pi together. So I'll leave you with that.
We have a question from a 10-year-old. His name is, or her name is Rid, and they ask, how did you come to like math? I would say, how did you come to love math, and why do you love math?
What I loved about math when I was 10 years old was that you could take a problem, even an arithmetic problem, like a multiplication problem, and do that problem lots and lots of different ways. But if you were careful, you would always get the same answer. And I found that consistency of mathematics to be absolutely beautiful then, and I still do now as a mathematician. And I not just doing arithmetic problems, but like I'll say, like oh, there's, like, why should the Pythagorean theorem work the way it works, right? And I love the fact that there are literally hundreds of explanations for why the Pythagorean theorem works. Why, but it started with me. You're at age 10 with arithmetic problems, and that I could do a problem lots of different ways and always get the same answer. Gosh, let me do one quick example. Svetlana, would you give me a 2-digit number and another 2-digit number, and I will multiply them, and I'll show you the process. Maybe more than one process for doing them. Most problems can be done lots of different ways. Svetlana, give us a 2-digit number.
53.
53, okay. And another 2-digit number.
98.
98, great. Okay, so how do we do 53 times 98, which, by the way, is 5,194, all right? And let me show you at least 2 different ways of doing that problem, okay? I'll save the clever way for last. But 53, now that's a prime number. You can't factor 53. I wish we could. I like factoring numbers when I can. But it's 50 plus 3. And 50 is a great number because it's half of 100. So if someone says, what's 50 times 98? I could think of, you could do 5 times 98. 5 times 90 plus 5 times 8 attaches 0, and you get 4,900. If you know half of 98 is 49, you could say, 50 times 98 is half of 100 times 98. It's half of 9,800 is 4,900. And you could do 3 times 98. 3 times 90 is 270. 3 times 8 is 24. I add them to get 294. And now the hard part, adding those 2 numbers together, if you do it left to right, you get 5,194. But there's a better way to do this problem, I think. I'm going to take advantage of 98. Now, I could factor that as 7 times 7 times 2. I can multiply 53 times 2 to get 106, times 7 to get 742. Then I have to multiply that by 7 to get 5,194. That's not the way I'm going to show you. Instead, I'm going to say 98 is 100 minus 2. So I'll do 53 times 100. What's that? That's 5,300. And then 53 times 2 is 106. Now it's 53 times negative 2. It's negative 106. And what's 5,300 minus 106? Well, if I subtract 100, I get 5,200. And if I subtract 6 from that, I get 5,194. And there it is. So you could take a problem, do it lots and lots of different ways. And if you're careful, you always get the same answer. And if you make a mistake, if the answers don't match, that means that at least one of your processes was wrong. And that could be educational in itself. You become a better problem solver by trying to say, well, I got 2 different answers. Where did I go wrong? I had to go wrong somewhere. And anyway, I find that that at least was what got me excited about math, as well as just all the beautiful patterns that numbers satisfy. I mean, we teach mathematics as an exercise in disciplined thinking, right? Put down the 1, carry the 2, don't ask questions, just do the process. And that's a surefire formula for turning people off of mathematics. I wish we would use math as more of an exercise in creativity, not just solve the problem, but solve the problem in more than one way, because that's life. That's the real world, right? It's sometimes there are easy solutions to problems, hard solutions, creative solutions, think outside the box solutions. And I don't think anything trains you to think outside the box more than mathematics.
And I want to pick up on something you I think maybe didn't make explicit, but it also dovetails a question that was asked, which is How do you feel when you make a mistake?
Oh, yeah.
And how should a student of mathematics feel when they make a mistake?
I make mistakes all the time. I try not to make mistakes when I'm doing my shows, but it happens. I'm human. Mistakes are an opportunity for learning. You learn by your mistakes. Not, nothing can keep you. Nothing can keep you held back more than the fear of making mistakes. At some point, you have to dive in and do it, and be prepared to make mistakes. It's a necessary process to get good at something. And I'll give you an example from my own personal life. I'm really not. I'm a terrible cook. Okay, but for many, embarrassingly many years, I just wouldn't cook. I would not cook for my family because I was just so sure that I would screw up. It's one thing to make a meal for myself. It's another thing when other people have to eat it. And ultimately, I had to take my own advice. I had to eat my own advice, right? Which is, so just try something. It's not going to come out perfectly the first time. It's not going to come out perfectly the fourth or fifth time, but you are going to get better at it. And eventually those mistakes will be less and less. So I think if you're just so afraid to ever get out there, whether it be a home activity like cooking, or you're afraid of bowling or tennis or chess, like, oh my gosh, you could be paralyzed with fear that I can't do anything because I'm not sure it's right. Just go in there and do it and learn from your mistakes. And the people who are most successful academically, I would argue in life, are people who have failed a ton. They've succeeded maybe 2 tons, but they've failed a lot. And the point is, they're trying things, they're putting themselves out there, and they're learning from the experience. So mistakes are a necessary part of mathematics and life.
So this would be just a perfect note to end on, but no, because we have the grand finale.
Oh, okay.
So,
All right, I'll tell you what. So,
Dr. Benjamin, the great Benjamini, I turn the floor to you for the grand finale.
all right, I'll do something. Earlier, you saw me squaring 2-digit, 3-digit, 4-digit numbers. I'm going to try, because I think this audience will be kind, I'm going to try to square a 5-digit number. But to make my job more interesting for you, as well as for me, I'm going to do this last problem thinking out loud. So you can actually honestly hear what's going on in my mind while I do calculations of this size. Unfortunately, this is going to prompt even more questions. We could have another hour to go on to what I'm doing here. But before I do this, let me just say one thing, because obviously we could spend several hours together, and there's so much we can talk about. And thank you for inviting me here today. If you are interested in learning about this, you can. I've got 2 books that are very inexpensive. You can find them online, Amazon, anywhere great books are sold. One is called Secrets of Mental Math, which is everything I know about doing math in your head. Co-authored by Michael Shermer, right, who has spoken. I saw him speaking to your group before. And my other book, it was Svetlana mentioned in the introduction, takes us from arithmetic to that next stage of math, the middle school and high school level math, called The Magic of Math, Solving for X and Figuring Out Why. I've also created 5 video courses for the Great Courses. If you subscribe to the Great Courses Plus, you can see them all for free. If you are interested in purchasing any of these DVD courses, send me an email. Svetlana will post it. It's benjamin@hmc.edu. HMC is Harvey Mudd College, where I teach. And I can offer you those DVD courses at a substantial discounted price. Okay, so anyway, so I'd like to end with the squaring of a 5-digit number. Svetlana, I'll ask you or somebody to give me a 5-digit number, and I will try and square that number in my head, and you can hear what's going through my process.
Okay. The number is 23,019. So 23019.
That's going to be kind of easy because of that 0, but
oh, fine. Let's put in a 5 instead of a 0. Let's do a 5 instead of
that. All right, because then it almost becomes like squaring two-digit numbers. All right, 23,519 squared. Great. Whoop. Let me explain to you how I'm going to attempt this problem. I'm going to break the problem into 3 parts. I'll do 23,000 squared plus 519 squared plus 23,000 times 519 times 2. Add those numbers together and with any luck arrive at the answer. Now let me explain one more thing. While I do this calculation, when the problems get really large like this one, I use a phonetic code which temporarily turns some of the numbers that I calculate into words. You'll know what I mean when I get to that. I just don't want you to think you're seeing something crazy happening up here. There's definitely a method to my madness, and it's explained in my books if you really want to know the details. But anyway, without any more stalling, here we go. I'll start the problem in the middle with 23 times 519. 23 times 500 is 11,500. 23 times 19 is actually 21 squared minus 4 is 437. So I get 11,500 plus 437 is 11,937. Double that to get 23,874. 23,874 becomes name faker. I'm going to keep it clean. Name faker is 23,874. Okay, next, I haven't said any part of my answer yet, but I'm about to. Name faker. Okay, next I do 23 squared, which is 529. Add that to name, 529 plus 23, I see a carry coming, is 553 million. Faker, faker. Okay, next I do 519 squared. That's 500 times 538 plus 19 squared is 269,361. Machete if I need it. Machete. Take the 269, add that to faker to get, oh boy, 143,361. I hope so. Thank you very much. My name is Arthur Benjamin, and I hope you enjoyed Mathemagics.
Thank you so much. It was just a delight, like I haven't experienced in a long time. What a way to start the new year. Thank you so much.
Happy New Year, everyone. And
thank you.
I hope our paths cross again.
Indeed, indeed. Goodbye.
Cheers.
And before I let you go to coffee, I want to share a quote by Katherine Johnson, who died recently at the age of 102. She was a pioneering Black woman mathematician who was one of NASA's human computers and an unsung hero of the space agency's early days. She said, "We will always have STEM with us. Some things will drop out of the public eye and will go away, but there will always be science, engineering, and technology, and there will always, always be mathematics." Thank you for joining us. Thank you very much to Dr. Arthur Benjamin for sharing some timeless magic math, and have a wonderful rest of your Sunday.